Hello and welcome back to the course. So we're still talking about the Laplace transform. Today we're going to talk about convolution, and this is section 6.3 in the book, and you can get the book, this URL. The link is in the description, and at that link you can browse the book as on the web. You can get a PDF, or you can buy a paperback if you want. All right, so the Laplace transform is not Laplace transform of product is not the product of the transforms. That's not true. But something of, they don't quite have a product of functions, but if the transform of something is the product of the transforms, and this something is actually almost like a product, and so that's convolution. So so here's what it is. So if you have two functions defined for positive time, we're doing Laplace transform after all, we have a new function f star g, and again it's a function of time, again for positive time t, and it has this formula, right? So basically what we're doing is we're taking f and we're looking at all its values from 0 to t, right? And then we look at g, and we kind of look at its values in the opposite direction, and we multiply, we take products of f and g at these two different points, and then we integrate, right? So here, notice that this is the tau, not t. So we're integrating with respect to tau, and so the t is right here, right, in this formula. Okay, now if you've seen convolution before, you might have seen this formula. It's almost the same, except the limits are different. So it's actually everything's the same if you just think of these functions as defined to be 0 for negative time, right? So normally for Laplace, we're only interested in positive time, right? So if you just make it 0 for negative time, you get this formula, but it's it's really the same thing. So if you haven't seen this, don't worry about it. We're just going to use this formula over here. Okay, so let's do an example. E to the t and t, right? Again, just think of those functions for positive time. And so the convolution of those, this function f star g, well, we just plug in, right? We plug into this formula. F is e to the t, so we have e to the tau, right? And then t, I plug in t minus tau, right? So I get this, right? And we just compute. Okay, integration by parts, so we skip that, and we get e to the t minus 1, right? So it's a function of t. That's the convolution for this guy. All right. Now let's do sine of omega t and cosine of omega t. Right? Omega is some constant. Again, for positive time. So again, we just plug in, right? So so this t that becomes the tau, right? And this t becomes the t minus tau, right? And we integrate. And this guy is easiest to do by changing this via this trig identity. So the inside is just equal to this. And now notice this is actually rather easy to integrate. Notice that we're integrating in tau, right? So there's a t here, so it's just this first sign is just a constant actually. So we're really just integrating one of these. So that's going to become a cosine. Okay, so let's see what it becomes, right? So we have this first term that's just multiplies by tau, really, and then the second term that has this, right? Now, if I plug in tau equals 0, the first term just goes away, and when tau is t, okay, I get 1/2 t sine of omega t. Okay, now the second term. So let's do. Let's first plug in t, right? So I have gonna have 2 omega t minus omega t, right? So it's gonna be omega t, right? And I'm subtracting this with tau set to 0, so it's gonna be cosine of minus omega t over here. But cosine of minus omega t is the same thing as cosine omega t, so that cancels. So we only just get the first term over here, right? 1/2 t sine of omega t. All right. And again, everything, just think of everything as undefined for negative t. So we're just looking at positive t. All right. Now convolution is like a product. It has all the sort of typical properties that a product would, right? I'm commutative, so S star G is G star F. If I multiply by a constant, so V times F star G is the same thing as multiplying by the G by a constant, or taking a convolution and then multiplying by a constant. I have the distributive law, right? F plus G star H is F star H and G star plus G star H, right? And it's associative, right? So I can do this in any order if I am if I'm convolving several things at once, right? So, and these are just these are just proved by calculus, right? You could just go through and just write down these integrals on both sides and see that they're actually the same, no matter what the functions are. All right. Now, for us, the most interesting property about the convolution is the following: that let's suppose that we have exponential order functions, just so that the Laplace transform exists. Then so is f star g, right? So f star g is also of exponential order. And if I take the Laplace transform of f star g, right, that's just what it is, right? Then it is equal to the Laplace transform of f times the Laplace transform of g, right? So the Laplace transform of a convolution is the product of the Laplace transforms, right? So that's the right thing, right? So there's a short way of writing it. If we're writing uppercase letters for uh, for the transforms. So we could also think in reverse, right? I mean, I'm just taking this formula and writing its reverse, right? So if I take the Laplace inverse transform of a product, it's the convolution. So let's see an example. So let's suppose we want to find the inverse Laplace transform of this guy, which really is just a product, right? I mean, I've really written it as a product. So, well, we could recognize these two inverse inverse Laplace transforms, right? So I know how to take the inverse Laplace transform of 1 over s squared, and I know how to take the inverse Laplace transform of 1 over s plus 1, right? And so the inverse Laplace transform of the product, right, is the convolution of t and e to the minus t, right? So it's this guy, almost like the thing that we just saw, right? Again, it's just integration by parts. This is really just this minus sign that's being a little annoying, and so we get this formula over here, right? Okay. Now let's see how it relates to differential equations. So if we have this formula over here, let's take the just the zero initial conditions, right? So we have this differential equation. Then if we apply Laplace to everything, we get this algebraic equation, right? And we could solve. We were doing this before, right? We could solve for capital X, right? So for the Laplace transform of the solution, right? And you have this guy over here. Notice that it's a product, right? And this guy 1 over s squared plus omega naught squared, that's the transfer function, right? That we've seen before. and its inverse transform is sine of omega naught t divided by omega naught, right? So it's almost the sine, right? So if we want to find little x, right, the actual solution to this equation, then well we want to invert this guy, which is this guy, which is, that's h of s times f of s, right? So if I know h of s, I know f of s, right? We're just inverting that, so that's the Laplace inverse transform, or inverse Laplace transform of a product h times f, right? And so we use convolution, right? So you write x as a convolution. Now, I mentioned this before, S star G is G star F. So we could write this in two different ways, right? Could write it like this, and you could write it like this. Sometimes one is more convenient than the other, but they're the same thing, right? So let's see how this handles resonance. So suppose that F is cosine omega t, right? Then we just plug in, right? Let's plug into this this formula over here, right? They're both the same. Let's just use this one. So we have x of t is just this thing over here. I'm just gonna pull out the omega naught. We get this convolution, and before we solve this, um, so we found what this was. So we just have this 1 over omega naught in there, right? But this convolution, that was precisely this t sine omega naught t, right? So we have this, right? And so we see that because of the t, this keeps growing, right? So that's resonance, right? So that's how, so here we didn't really have to worry about treating resonance separately. That just sort of came naturally, right? It all has the same formula, this one or this one. Right? Now notice that I have the solution written as definite integral for any f. I could just plug in, now that I have this solution, I basically solved it for all different f, right? I can just start plugging in different f's, right? And get different solutions, right? Or even if I couldn't quite get these solutions analytically, maybe I can get them numerically at least, right? I have a nice formula, right? A calculator or a computer is gonna be very happy about computing these things for any particular t. All right, so the general idea is if I have a constant coefficient equation, some operator L of x, so it's linear constant coefficient differential equation with an arbitrary right-hand side and with zero initial conditions. So you find the transfer functions of a transfer function h, right? Then x is h times the Laplace transform of f. So if you find the inverse Laplace transform of h, right, you would get that little x is well, the inverse Laplace transform of the Laplace transform of x, which is just capital F times capital H, which is just the convolution of f and h, right? And so it's this guy, right? So basically, we didn't really have to, go back and forth. What we really just need to find the transfer function, right? Find its inverse transform, and then we have a formula for any f. So we don't have to get capital F really to write down this formula, right? So we really solved for any forcing function. Once you know this little h, you have a nice formula for the solution for any forcing function little f, right? For any right-hand side. Okay. Now, convolution sometimes appears in integral equation. For example, this is the Volterra integral equation. So I have an equation like this, and here f and g are some known functions, right? So those are given, and x is the unknown, and I'm trying to find the x, and it's the x appears under the integral here, but you notice that this is a convolution, right? So we can apply Laplace, and we're gonna get capital X over here, then we're gonna get capital F, and this convolution just becomes a product, the capital G times capital X, right? And so we can just solve for capital X, right? And then we invert, right? So for example, suppose that we have this, right? So little f was e to the t, g was the hyperbolic sign, and we're trying to solve for x, right? So we apply Laplace, we get 1 over s plus 1 for the e to the minus t. We get the hyperbolic sign becomes 1 over s squared minus 1, and well, x is of course x, right? So we solve for capital X, which is just this thing once we simplify, which we do partial fractions, and then we just look at the table and we invert, right? And we get this thing, right? And that's the solution. That's the x that solves this equation, right? All right. So we've seen what's the right product that that goes forward as a product on the Laplace transform side, right? So it's the convolution. So the Laplace transform of a convolution is a product of the transforms, right? That's the thing to remember, right? In other words, the inverse Laplace transform of a product of transforms is the convolution of the functions, right? And the convolutions is, there's nothing scary, just a simple formula, right? Formula like this. All right. So next time, what we'll look at is the Dirac delta function and how that how that behaves with the Laplace transform. And by the way, Dirac delta function is not a function, but it's almost a function. As far as the engineers are concerned, it's a function, right? But it's not really a function. But it's something that you can integrate, so it's something that works well with integration. Well, with Laplace transform, it's basically the derivative of the step function. All right, so we'll talk about that next time. So see you then.